For most of human history, we imagined the universe as scattered islands of galaxies floating in endless dark. But when astronomers began charting the cosmos in 3 dimensions, a breathtaking pattern emerged. The universe wasn't random at all. It was woven. Across billions of light years, galaxies and clusters form long, glowing filaments, the cosmic web. Between those filaments lie enormous voids, almost empty, stretching hundreds of millions of light years across. These aren't poetic metaphors. They're real structures, revealed through decades of sky surveys and simulations that trace the faint glow of ancient matter. The story begins with the early universe, roughly 380,000 years after the Big Bang. At that moment, light could finally travel freely through space. Tiny ripples in density imprinted on this early light we now call the cosmic microwave background became the seeds of everything that followed. Over billions of years, gravity pulled denser regions together, while dark energy pushed space to expand. The result was a vast network of filaments and nodes where matter gathered like dew along invisible threads. These cosmic highways carry gas, dark matter, and entire galaxies, connecting them in a grand structure that spans the observable universe. To visualize it, scientists turn to some of the largest simulations ever run projects, like the Millennium Simulation, Illustris, and more recently, the TNG-50 model. Each begins with known physics, gravity, gas dynamics, and the mysterious influence of dark matter. Over cosmic time, those simulations grow from a smooth fog into an intricate web. The accuracy is astonishing. When astronomers compare the simulated web to real galaxy maps, the resemblance is nearly perfect, suggesting that our understanding of large-scale structure is on the right track. Yet here's where the wonder deepens. We can't see most of it. The cosmic web is built largely from dark matter, an invisible substance that neither emits nor absorbs light. We infer its presence by the way galaxies move, or how light bends when it passes through. Where dark matter is densest, ordinary matter follows, forming stars and galaxies along the same threads. In this way, dark matter acts like scaffolding for the visible universe, shaping everything we can observe while remaining hidden itself. When you zoom out far enough, the Milky Way is just one dot along one strand of this immense network. Our entire galaxy, and thousands of others nearby, belong to a filament that stretches through a region known as the Laniakea supercluster, a gravitational domain containing over 100,000 galaxies. These filaments connect to others, weaving an almost organic architecture that gives the universe its structure on the largest scales. Astronomers describe this pattern as cosmic foam. Filaments form the walls of vast bubbles, and inside those bubbles are the empty voids. Some of these voids span hundreds of millions of light years, nearly devoid of galaxies. And yet, even there, faint traces of gas and dark matter persist, reminders that no part of the cosmos is truly isolated. Everything is connected by the web's invisible threads. If we could somehow see the entire structure at once, it would look like a living organism, veins and arteries carrying the flow of matter and energy across the universe. It's a reminder that what seems separate, each galaxy, each star, even us, is part of a vast interconnected whole written into the fabric of space itself. And as we explore deeper, one question emerges. How exactly did this cosmic web form such perfect order out of primordial chaos? When astronomers first began to chart galaxies beyond the Milky Way, they expected a random scatter across the sky, a uniform sea of light without pattern or purpose. But the more data they gathered, the more the illusion of randomness dissolved. What they found instead was astonishing. Galaxies were not evenly spread, but clustered together in great sheets and filaments, leaving vast empty gaps between them. These early hints came in the 1,970 seconds and 1,980 seconds from redshift surveys, which measured how much a galaxy's light stretched as the universe expanded. Each redshift corresponded to distance, allowing scientists to build three-dimensional maps of the cosmos for the first time. The first large-scale survey to truly reveal this hidden order was the CFA Redshift Survey. When its results were plotted, the pattern looked eerily familiar, like a cosmic sponge, with dense clusters forming along walls and filaments surrounding enormous voids. Later projects, such as the Sloan Digital Sky Survey, expanded this view to millions of galaxies, confirming that the universe has structure on scales far beyond what anyone had imagined. Instead of chaos, astronomers saw a web-like geometry stretching hundreds of millions of light-years in every direction. Each point on these maps represents an entire galaxy, yet when connected, they outline the same intricate network seen in computer simulations of dark matter. It was one of the most important confirmations in cosmology that the invisible scaffolding predicted by theory actually matched what telescopes observed. To visualize it, scientists often liken it to a vast 3D spiderweb made of gravity, where galaxies gather at the intersections. Cosmic nodes and filaments act as bridges connecting them. But observing the web directly is almost impossible. Most of it is invisible, made not of stars or glowing gas, but of dark matter and intergalactic plasma so thin it barely emits light. To detect it, astronomers had to invent new methods. One approach was gravitational lensing, measuring how light from distant galaxies bends as it passes through invisible mass. These subtle distortions act like fingerprints of the unseen, revealing the hidden distribution of dark matter. Another method came from tracing the faint glow of hydrogen gas illuminated by distant quasars, whose intense radiation lights up the cosmic filaments like a flashlight shining through fog. By combining these techniques, scientists gradually built a clearer picture of the web's skeleton. They discovered that the largest filaments span up to 1 billion light-years, while smaller ones connect clusters like bridges in a galactic city. Between them are voids so vast that if the Milky Way sat at their center, we might see almost nothing for hundreds of millions of light-years in any direction. And yet, these voids play a crucial role. They provide the contrast that makes the filaments stand out, like the dark between stars. As technology improved, telescopes and surveys began mapping these structures in unprecedented detail. The Baryon Oscillations Spectroscopic Survey and its successors measured how galaxies clump on cosmic scales, giving scientists a ruler for the expanding universe itself. Each discovery refined the picture of a cosmos shaped not by random chance, but by physics working over unimaginable timescales. Today, when we look at the largest 3D maps of the universe, the resemblance to biological or neural networks is striking. From a handful of early redshift measurements, humanity has learned to read the pattern of everything, the web that binds galaxies, matter, and perhaps even the fate of the universe itself. The cosmic web may look static when mapped, but in reality, it's alive with motion. Gravity is constantly at work, pulling gas and dark matter along those invisible filaments, feeding galaxies and clusters like veins supplying a living organism. Every filament is a channel of cosmic traffic material drifting, colliding, and condensing across millions of light-years. To understand how galaxies form and evolve, astronomers had to uncover how this hidden flow works. At the heart of each filament lies a backbone of dark matter. Though invisible, it provides the gravitational glue that keeps ordinary matter from dispersing into the void. Gas collects along these spines, gradually cooling and condensing as it moves toward regions of higher density. Over billions of years, these streams of matter converge at intersections, the nodes of the web where galaxy clusters form. These are among the most massive structures in the universe, bound together by the same gravity that sculpted the web itself. Computer simulations have allowed scientists to watch this process unfold across cosmic time. They reveal a universe that behaves more like a fluid than a solid structure. Filaments twist, stretch, and merge as new galaxies are born and old ones drift apart. Hot gas flows along them like rivers of light, glowing faintly in X-ray and ultraviolet wavelengths. these simulations don't just look beautiful. They help scientists test real physics, measuring how temperature, pressure, and gravity shape the web's architecture. For decades, astronomers suspected that a significant portion of the universe's normal matter, the kind that makes up stars, planets, and us, was missing from their calculations. Observations of galaxies and clusters could only account for about half of the expected baryonic matter. The rest seemed to vanish. Then, with advanced X-ray telescopes and spectrographs like ESA's XMM Newton and NASA's Chandra Observatory, astronomers began detecting faint signatures of warm-hot gas spread across filaments. This elusive material, known as the WIM, the warm-hot intergalactic medium, could account for much of the missing matter. It doesn't shine brightly enough to see with the naked eye, but its fingerprints appear when quasar light passes through it, subtly shifting the light spectrum. These discoveries reshaped our understanding of how galaxies grow. The cosmic web is not just scaffolding, it's a delivery system. Streams of gas flow along filaments, feeding galaxies the raw material needed for star formation. Without this continuous inflow, galaxies like our Milky Way would have run out of gas long ago. In some regions, the flow is so consistent that galaxies align with the direction of their filament, like trees bending toward a prevailing wind. But the web doesn't flow endlessly. Gravity competes with expansion, and over time, the universe's accelerated growth stretches these filaments thinner. For now, they remain the lifelines of the cosmos, silent rivers connecting every point of light in the sky, moving matter across an ever-expanding universe. For most of the universe's history, the cosmic web remained invisible, a structure known only through simulations and indirect clues. The challenge was simple to describe, but nearly impossible to solve. How do you find something that doesn't emit light? The filaments connecting galaxies are made mostly of dark matter and thin gas, far too faint for traditional telescopes to capture. Yet astronomers knew that if the web truly shaped the cosmos, there had to be a way to see its shadow, to catch the faint glow of the invisible. The breakthrough came from an unexpected direction. Quasars, the brilliant hearts of distant galaxies, powered by supermassive black holes. Their intense radiation cuts through intergalactic space, and as it passes through the cosmic web, some of that light is absorbed by hydrogen gas along the way. This leaves a pattern of dark lines in the quasar spectrum known as the Lyman alpha forest. Each line marks a region where the light encountered a cloud of gas, providing a kind of barcode of the web's structure. By studying thousands of quasars, astronomers began reconstructing a 3D map of hydrogen across the universe, the first rough glimpse of the cosmic web itself. But quasars alone weren't enough. Their light is too sparse, like shining a few flashlights through a fog and trying to guess the shape of the mist. To fill in the picture, astronomers turned to a newer technique called gravitational lensing. When light from a distant galaxy passes near massive structures like a cluster of galaxies or a dense filament, the fabric of space-time bends, distorting and magnifying the light. By measuring those distortions across millions of galaxies, scientists can infer the invisible distribution of matter, including dark matter. The results have been astonishing. Observations from instruments like the Hubble Space Telescope and the Subaru Hyper-Suprime Cam have revealed long, filamentary patterns of mass stretching between clusters, ghostly bridges that match predictions almost perfectly. Then, in 2019, astronomers made one of the first direct detections of a filament itself. Using the MUSE instrument on the Very Large Telescope in Chile, a team observed faint hydrogen gas glowing in ultraviolet light, illuminated by nearby quasars. What they saw was breathtaking, a strand of the cosmic web spanning over 10 million light-years, shimmering softly against the dark. For the first time, humanity had seen one of the threads that binds the universe together. Other telescopes soon followed. The Keck Observatory captured similar filaments glowing faintly in Lyman alpha emission, while X-ray observatories like Chandra and Rosetta began to trace the hot gas flowing along them. Each detection confirmed what simulations had long suggested, that the web is real, dynamic, and luminous in its own quiet way. What had once been theoretical had become visible, a ghostly structure stretching across time and space. Yet even with these discoveries, most of the cosmic web remains hidden. Its light is so faint that even our best telescopes struggle to detect it. That's why astronomers are developing new observatories, ones designed specifically to chase the glow of the intergalactic medium. Instruments like the upcoming Nancy Grace Roman telescope and the European Space Agency's Athena mission will map these faint filaments with unprecedented precision. For the first time, we may soon see the full anatomy of the universe, a network of glowing bridges connecting every galaxy, every cluster, and perhaps every atom of matter we know. The cosmic web we see today is the culmination of nearly 14 billion years of cosmic evolution. But its story began long before galaxies, stars, or even atoms existed. In the first instant after the Big Bang, the universe was a chaotic ocean of energy. Matter and radiation were intertwined, dense and uniform. Only tiny fluctuations, 1 part in 100,000, rippled through that early plasma. These imperfections, random as they seemed, would become the blueprint for everything that followed. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen, and light was finally free to travel. This ancient glow still surrounds us today as the cosmic microwave background. When scientists study its subtle variations, they see a map of the universe's first density differences, the very seeds of the web. Where matter was slightly denser, gravity pulled harder, drawing in more gas and dark matter. These regions grew over time, forming the first filaments and clusters, while the emptier regions stretched into vast voids. Fast forward hundreds of millions of years, and those tiny ripples had become sprawling tendrils. Gravity and time transformed simplicity into structure. The first galaxies lit up along the densest filaments, forming cosmic neighborhoods where matter gathered most efficiently. Dark matter, invisible but dominant, dictated the rhythm. Wherever it condensed, normal matter followed. The earliest stars formed in these regions, their light marking the end of the cosmic dark ages and the beginning of the reionization era, a time when ultraviolet radiation cleared the fog that once filled space. Computer simulations show this transformation with haunting clarity. In the early universe, the web was a faint, delicate lattice. Over billions of years, as galaxies merged and clusters grew, the web thickened and brightened. Filaments became highways of matter transfer, feeding clusters at their intersections. In this sense, the universe behaves like a living system, not static, but continuously changing as new stars form and old ones die, as energy and matter flow between the filaments and the voids. Interestingly, the web's evolution reveals the influence of dark energy as well. Around 5 billion years ago, the universe's expansion began to accelerate. The pull of gravity weakened compared to this mysterious repulsive force, causing the largest structures to drift apart faster than before. The filaments still channel matter toward clusters, but the process is slowing. Simulations predict that in the distant future, galaxies will continue forming only in isolated pockets, while the rest of the universe fades into separation and stillness. The cosmic web, once vibrant with motion, will eventually grow cold and quiet. To trace this entire story, astronomers combine data from across the electromagnetic spectrum microwave observations to study the earliest light, optical surveys to map galaxies, and X-ray and ultraviolet measurements to trace hot gas and plasma. Together, these layers reveal the web's evolution, not as a static sculpture, but as an ongoing film, stretching from the birth of time to the distant future. Every filament, every cluster, every void carries the memory of that first ripple, a faint echo of the universe's earliest heartbeat, frozen across the expanding cosmos. The cosmic web doesn't just shape where galaxies form, it also influences how they grow, move, and even rotate. Galaxies are not scattered randomly through space. They follow the invisible framework laid down by dark matter, often forming in filaments that act as gravitational highways. These filaments guide the flow of gas, the migration of galaxies, and the direction of their spin, creating patterns that stretch across cosmic scales. What we see as isolated systems, the Milky Way, Andromeda, or any distant spiral, are in reality shaped by the unseen geometry of the web around them. Astronomers discovered this influence by comparing simulations to real surveys. In the early 2000s, large redshift studies like the Sloan Digital Sky Survey revealed that galaxies inside filaments were not only denser, but also aligned in similar orientations. Their axes pointed along the same direction as the filament itself, as if responding to a common gravitational current. In contrast, galaxies inside the vast voids tended to spin in more random directions. The data suggested that cosmic structure exerts a subtle but powerful influence, a kind of gravitational choreography written into the background of space. This alignment is not limited to spin. The cosmic web also affects how galaxies feed and evolve. Streams of cold gas flow along filaments into galaxies, replenishing the fuel needed for star formation. Without these streams, galaxies would quickly run out of material and fade into dormancy. In regions where filaments intersect, multiple streams converge, producing giant clusters rich in hot gas and starburst activity. These intersections, called nodes, are some of the most energetic places in the universe, where gravity, heat, and magnetic fields collide in a cosmic dance that shapes galaxy evolution. Even the environment within a filament determines the kind of galaxies that thrive there. Observations show that galaxies embedded deep inside filaments are often larger and older, with slower star formation, while those at the edges are younger and bluer, still forming stars at a rapid pace. The difference reflects how gas flows smoothly in some regions, turbulently in others, sculpting the growth of each galaxy over billions of years. In this way, the web acts as both architect and sustainer, setting the stage for the diversity of galaxies we see across the sky. New simulations like Illustris TNG and Eagle have added an even more fascinating detail. The cosmic web appears to influence the rotation of galaxy clusters themselves. These massive systems, containing thousands of galaxies, sometimes show coordinated motion, like giant eddies in a galactic ocean. The filaments connecting them act as channels for angular momentum, the property that governs spin. This suggests that from the smallest scales of individual galaxies to the largest superclusters, the same physical laws of motion and flow are at work. Our own Milky Way is part of this grand alignment. It sits within a filament of the Laniakea supercluster, connected to nearby groups and clusters through strands of dark matter and gas. The way our galaxy rotates, moves through space, and draws in material is all shaped by this vast network. Even now, invisible rivers of matter continue to flow toward us along those threads, sustaining our galaxy's life cycle in a process that began before the Earth itself existed. When we step back and view the universe as a whole, it's not a random scatter of galaxies, it's a masterpiece of balance and pattern. The cosmic web forms an intricate tapestry, a network of glowing clusters and vast, empty voids stretching for billions of light years. Like the stitches of an invisible loom, gravity has woven this structure over cosmic time, shaping where galaxies thrive and where silence reigns. Every cluster, every filament, every gulf of emptiness tells part of the story of how the universe built itself from chaos into order. Clusters sit at the crossroads of this great design, intersections where filaments converge and gravity reigns supreme. They are the universe's cities, dense, crowded, and filled with activity. A single cluster can contain thousands of galaxies, trillions of stars, and unimaginable amounts of dark matter. These clusters are surrounded by halos of scorching gas that glow in X-rays, a signature of the intense gravity binding them together. Inside, galaxies collide, merge, and transform, creating new stars and triggering supermassive black holes to flare to life. In a cosmic sense, clusters are living entities, dynamic, evolving, and constantly exchanging energy with the filaments that feed them. But between those bright knots of matter lies the opposite extreme, the voids. These are vast regions of near nothingness, stretching across hundreds of millions of light years. Inside them, galaxies are rare and faint, drifting quietly through emptiness. To astronomers, voids are just as important as clusters. They act as laboratories of cosmic expansion, regions where dark energy dominates and gravity has little to counter it. By studying how galaxies move near the edges of voids, scientists can measure how fast the universe is stretching, offering vital clues about the nature of dark energy itself. This contrast between dense clusters and empty voids defines the large-scale geometry of everything we can see. The universe is not uniform. It's a cosmic sponge, where dense filaments and hollow gaps form a repeating pattern on unimaginable scales. This pattern follows the mathematics of fractal structures that repeat their forms at different levels of magnification. Whether you look at a single galaxy group or an entire supercluster, the same branching structure appears. It's nature's code, written across billions of light years. Simulations and surveys have made this visible in astonishing detail. The Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have mapped millions of galaxies, revealing a three-dimensional structure that looks almost biological, like neurons in a brain or roots of a tree stretching through space. The resemblance isn't poetic coincidence. Both networks form from the same principle of efficiency connections growing, where energy and matter can flow most easily. The universe, it seems, builds itself using the same logic life does. And this tapestry isn't static. Over time, clusters grow heavier, filaments stretch thinner, and voids expand wider. Dark energy is slowly pulling the threads apart, reshaping the pattern we see. In the distant future, clusters will drift so far apart that light from one may never reach another. The cosmic web will fade from view, leaving only isolated islands of matter surrounded by an ever-deepening void. Yet, for now, we exist at a special moment when the web is still visible, when light can still travel between galaxies, and when we can still map the grand design that holds the universe together. From our small planet, we're witnessing the cosmos at its most connected, just before its great unraveling. For most of human history, the cosmic web was invisible, a concept beyond even imagination. We could see the stars and galaxies, but not the vast network binding them together. Only in the last few decades have we developed the tools to truly reveal this hidden architecture of the universe. Mapping the cosmic web is like trying to chart an ocean by studying the ripples on its surface. What we can see, the galaxies, are just the luminous markers of a much larger, invisible current beneath. The first real breakthrough came from large-scale redshift surveys in the late 20th century. Instruments like the Sloan Digital Sky Survey scanned millions of galaxies, measuring how fast they were moving away from us. By turning redshifts into distances, astronomers could build three-dimensional maps of the universe. What emerged was astonishing: long chains of galaxies stretching like threads, with vast voids in between. These patterns matched predictions from dark matter simulations almost perfectly, confirming that we were finally glimpsing the skeleton of the cosmos. But galaxies only trace a fraction of the web's mass. Most of the universe, the dark matter and intergalactic gas that make up its backbone, emits no light. To see it, astronomers turned to gravitational lensing, a phenomenon predicted by Einstein's general relativity. As light from distant galaxies passes through massive structures, it bends slightly, like light through glass. By measuring these distortions across millions of galaxies, scientists can reconstruct the underlying distribution of dark matter. The result is a shadow map of the cosmic web, not of what shines, but of what truly shapes the universe. Next came the discovery of the warm-hot intergalactic medium, or WIM, a faint plasma threading between galaxies heated to millions of degrees. Though nearly invisible, it glows weakly in X-ray and ultraviolet light. With space telescopes like XMM Newton and Chandra, astronomers began detecting its signature, confirming that the web is not empty at all, but filled with a diffuse gas connecting everything. This gas holds much of the universe's missing baryons, the normal matter that had long been unaccounted for in earlier measurements. In other words, the web isn't just scaffolding, it's a living conduit through which the universe circulates its material. New technology has taken this mapping even further. The Dark Energy Spectroscopic Instrument is now charting the positions of over 40 million galaxies and quasars, creating the most detailed map of the cosmic web ever attempted. Meanwhile, radio arrays like LOFAR and the upcoming Square Kilometre Array are probing hydrogen across cosmic time, revealing how gas flows along filaments to form galaxies. These instruments work together like the eyes of a single giant observer, each wavelength revealing a different layer of the universe's hidden structure. Even artificial intelligence is entering the field. Machine learning algorithms can now identify filament patterns in vast datasets faster and more accurately than any human. They help predict where unseen dark matter should lie, guiding telescope observations and refining our models. For the first time, we're not just seeing the web, we're beginning to understand how it breathes, evolves, and interacts with everything within it. It's easy to forget that every image of the cosmos, every swirl of galaxies, every strand of light represents data painstakingly gathered across years of observation. But behind each image lies the story of technology itself. Human curiosity encoded in silicon and glass, reaching across billions of light years to uncover the structure that holds the universe together. The deeper we study the cosmic web, the more it reveals something profound, a reflection of patterns that echo far beyond astronomy. Across vastly different scales, from the neurons in a human brain to the filaments of galaxies spanning billions of light years, nature seems to favor the same design: networks of connection. These are not coincidences of appearance, but expressions of universal principles: efficiency, flow, and balance. The cosmos, it seems, organizes itself according to the same logic that governs life. Scientists at the University of Bologna once compared the large-scale structure of the universe with the neural network of the human brain. They found striking similarities. Both systems allocate roughly the same proportion of matter to connections versus nodes, about 30% dense clusters linked by 70% of empty space. Both optimize energy transfer through minimal pathways, forming patterns that emerge naturally when systems grow and evolve under similar physical rules. In a sense, the universe and the brain are both engines of information, one made of neurons, the other of galaxies. But the parallels run deeper than geometry. Galaxies exchange material through filaments, just as cells exchange nutrients through capillaries. Stars within galaxies live, die, and recycle their elements, enriching the cosmic environment the same way ecosystems on Earth sustain life through cycles of renewal. Even the distribution of dark matter mirrors the invisible infrastructure of life's dependencies, unseen but essential, providing stability without being directly observable. When scientists describe the cosmic web as the backbone of the universe, it's more than a metaphor. It's an acknowledgement that structure and interdependence are woven into existence itself. This understanding challenges the way we think about isolation. The universe, from its largest clusters to its smallest atoms, is a story of relationships. Every galaxy's motion depends on another's gravity. Every star's birth is triggered by the remnants of one that came before. Even the atoms in our bodies, the carbon, oxygen, and iron, were forged in stars that once flowed through these same filaments of matter. We are, quite literally, made from the web itself. The same network that binds galaxies together gave rise to the ingredients that make thought, emotion, and consciousness possible. Modern cosmology and biology both converge on one truth: connection drives evolution. Whether through gravity or genetics, systems grow more complex by linking with others. In the universe's early days, simple hydrogen atoms came together under gravity's pull to form stars and galaxies. On Earth, simple molecules came together under chemical forces to form life. Both processes obey the same fundamental tendency to organize, connect, and build something greater than their parts. Yet, The most humbling realization may be this: when we look at the cosmic web, we're seeing a structure that includes us. The same physical laws that shape galaxies shape our existence. We are observers, looking at the pattern that produced our own ability to observe. The universe, through us, is watching itself and understanding that may be the most profound connection of all. The more we uncover about the cosmic web, the more it blurs the boundary between the physical and the philosophical. The web is not just a map of matter, it's a portrait of process. Every filament, every cluster, every faint wisp of gas tells the story of how the universe transforms energy into structure, chaos into order, and emptiness into something that can think and wonder about itself. It's a reminder that the universe is not a static place. It's an ongoing act of creation. When scientists simulate the universe from its earliest moments, they start with tiny quantum fluctuations, minute ripples in the fabric of space-time. Over billions of years, gravity amplified these ripples into the filaments and clusters we see today. That means the cosmic web began as a pattern of potential, a field of probabilities collapsing into structure. It's a physical manifestation of growth, an expression of how small differences can become the foundation of complexity. Every galaxy in the night sky began as one of those ripples, a random whisper that gravity turned into light. As our instruments become sharper and our simulations more powerful, we keep finding new layers of order. The universe appears chaotic only from afar. Look closer, and symmetry emerges everywhere. Spiral galaxies obey mathematical ratios found in seashells. The clustering of galaxies mirrors the equations that describe sound waves and ocean tides. Even dark energy, the invisible force accelerating cosmic expansion, seems tuned with such precision that had it been slightly stronger or weaker, galaxies and life itself could never have formed. It's as if the universe walks a tightrope between creation and collapse, perfectly balanced on the edge of possibility. This balance has led scientists and philosophers alike to ask a profound question: is the universe fine-tuned for life? Or is life the natural result of a universe that must create structure to exist? One view suggests that countless universes may exist, each with slightly different physical laws. In most, nothing forms at all. But in ours, conditions happened to align, matter clustered, stars ignited, and consciousness arose to witness it. The cosmic web may therefore be more than an arrangement of matter. It might be the signature of a universe capable of reflection. If the cosmic web teaches us anything, it's that connection defines reality. Nothing exists in isolation, not galaxies, not stars, not us. The same gravitational threads that bind clusters together also shaped the atoms in your body. When you look up at the night sky, you're seeing the network. You're part of the same web that holds the Milky Way in its grasp, holds you, too, through every molecule of your being. And perhaps that's the most extraordinary revelation of all. The universe is not something happening out there. It's something we are within, a living, expanding whole, whose every thread leads back to the same origin. Every discovery we make about it is, in some quiet way, a rediscovery of ourselves. Because in the end, the cosmic web is not just the structure of the universe, it's the architecture of existence, infinite, connected, and still unfolding.